Can I put it oh, yeah.
It's
Here.
in the back it's better. Because otherwise...
There's, okay.
Yes.
Okay, let's do this. Like that. Okay. Okay. Thank you. Uh-huh. I think it's BV in perturbative EQ. That's what I remembered.
Yes. That's definitely.
Yeah, that looks right, yeah. I was hoping you remind me.
We're going to start the afternoon session with Kasja Rejzner that will talk about battalion Vierkovisky formalism in perturbative algebraic quantity.
Thank you. Thanks for the introduction and giving me an opportunity to participate in this event. Yeah, so I hope this is the title I gave, but it's definitely what I'm going to talk about. Okay, so you already had some BV from Pavel, so now it's the time to remind yourself everything you learned from Pavel's lectures and try to maybe connect this to what I'm going to talk about right now. So my aim is to cover some of the things that Pavel skipped, namely how to actually take seriously the infinite dimensional character of quantum field theory and do things like renormalization and still end up with relatively nice BV structure at the end. So first let me start with explaining the title a bit. So this is the algebraic quantum field theory story. This is something that goes back longish time to the 60s. So algebraic quantum field theory was originally thought out as an axiomatic framework for QFT. So here's the idea. So one would axiomatize QFT in terms of algebras of observables that you assign to regions of Minkowski spacetime. So this is a region of Minkowski. Minkowski, you should by now probably know, is R4 with the metric that for me has the following signature. Apologies to people who have different signature, but my sign convention is not entirely consistent anyway, so signs are not going to be terribly relevant in this talk. Okay, so here regions, and we want them to be bounded. Okay, and this is the algebra of observables. Okay. All right, so in the original framework, people would work with C-star algebras. So John already mentioned C-star algebras, so at least you've heard the word. And von Neumann algebras. Now, I'm not going to work with any of these, at least today. Maybe at the end, if we are going to have some time left. But this was the original setting. Okay, so now for this assignment, there are some axioms that one requires. So first one, so now let's write it like this, axioms. Axioms. So first one, if we have smaller region inside the larger region, then we want the algebra of observables of the one fit into the other. Okay? And then there is another one related to causality. So there has been a mixture of Euclidean and Lorentzian things during this school. Now I'm always working with Lorentzian, so causality plays a role. So in any case, other questions? So if people don't understand some things I'm talking about, then please interrupt me. So for example, if you don't know what the causal structure is or something like that, I don't know what your background is. So you might want to ask. Okay, so if I have two regions which are space-like separated, that's what this symbol means. So space-like. All right, and then it follows that the corresponding algebras should commute with each other. So somehow this tells us that observables in space-like regions, space-like, should be independent. So causality. So this is causality. Sorry? Sorry, what did you say? Directions of what? I'm not talking about Hilbert spaces at the moment. So this is really just the algebra of observables. So, that's right. That's what the first thing says. That's a good question, right? So, yes. So U1, O1, and O2 would live in a bigger, I mean, you can put a region around them, right? Yeah, so one. So, but that's an excellent question, actually, in terms of what happens next. So this should happen here. Okay, and there is another one. I'm going to write it here. Actually, no, I want to be symmetric, so I should start with this one on top. Okay. So if we have now a region with a Cauchy surface, all right, and then we take a neighborhood of a Cauchy surface. Let's call it N. This is O. Well, in classical field theory, in Lorentzian signature, sort of nice theories will have well-posed Cauchy problem, which means that solutions to field equations can be reconstructed from the Cauchy data in the neighborhood of the Cauchy surface. Now here we have something which is very similar, namely we require that A of N is equal to A of O. Okay, so that's actually quite strong. And there are more which I'm not going to talk about because they're not relevant to this story. What is N is a neighborhood of the Cauchy surface. It's just could be a color neighborhood, right? And N is within O. So that's the shaded region somehow. Right. Sorry? Great question. So Cauchy surface, sigma. So this is a hypersurface in, let's stay on Minkowski for a while, in M, such that every causal curve intersects it exactly once. So this is causal curve. Okay, so this is time-like or null. So the tangent vector is either time-like or null. A causal curve and intersects exactly once. Okay. Sorry?
Oh, future in the past.
So what is in the future? Yes. No, O is the whole thing. O is the whole double cone here. So O is not in the future. So O is this set, this one. Does it make sense? I didn't understand your question then. Yes. Yes. Cuts the complement of. No. Sorry, I don't understand what you're saying. So in Minkowski space-time, right, a Cauchy surface is, for example, time zero surface, right. and then any causal curve intersects it exactly once because you cannot go around. You cannot go, if you could go around and intersect it again, that, yeah.
I'm just saying the complement of sigma will be disconnected.
Complement, sure, yes. That's correct. That's a correct statement, yes.
And O is one of the components?
No, O is the whole set for whom sigma is the Cauchy surface. So you can, okay. So O is a subset of M, and here this is the Cauchy surface for O. So every causal curve contained in O intersects sigma exactly once. So obviously, yeah, if you take the complement of sigma in O, it will be disconnected. That's perfectly fine. I mean, there's not a problem with this. But yeah, okay, now I understood. So there's a lot of noise downstairs, so I don't always hear exactly the questions. Yes? No. Oh, no, it's just I like drawing them this way.
So what is the algebra defined?
Bounded regions of Minkowski spacetime. Any bounded regions, yes, that's correct, yes. Mm-hmm. So that's that, yeah. So that's a sort of original setting. Okay, any other questions? Yes? That's another very good question. So this is the sort of original AQFT framework where you actually are very strict with equal. So that's equal, not isomorphic, equal, okay? Now I'm going to throw it out in a second, so don't get attached to that equality sign. Because we have seen that equality is bad. Don't do that anymore these days. Okay, so that's the original setting. Now let's do perturbative AQFT. Okay, so and here, well, first I want to go something more general than Minkowski spacetime. So I'm saying that M is a globally hyperbolic spacetime. Okay, so what does it mean? It means that M is isometric to Cauchy surface cross R. So note it is non-compact even if the Cauchy surface is compact. All right, and these are good spacetimes to work on. Now, this regions, well, for general manifolds, that wouldn't make sense to say bounded. So all are now relatively compact opens. Okay. Again, I'm assigning algebras to them, but no, this is actually going to be something more general than that. So first of all, I'm dropping this C-star and von Neumann business entirely. So this is going to be a star algebra. So has an involution. I think that was already mentioned by John. What else? Well, topological. I want to have some convergence. Perturbative. Actually, you know what? I want to work with formal parameters. So I want to think of h bar as a formal parameter. So that would be formal power series with coefficients in these algebras. And then I remember I want to quantize gauge theories, and I want to use BV formalism for that. So actually, I need chain complexes in topological star algebras, power series in h bar. Okay, that's a mouthful. But there is a reason for all the pieces. Okay, so that you can see is way more general than the original stuff. Now, why did we do that to ourselves at all? Somehow, that framework is very nice, but the problem is producing models in 4 dimensions that describe interacting theories. Not to say, describing, say, standard model or QED, or things we actually care for in physics. So that is hard. People have not done it yet. We can do things in 2 dimensions, 3 dimensions, but 4 dimensions is difficult. So now, by allowing us a bit more flexibility in how we understand observables, we are actually opening up the possibility for constructing all these models. So I'm going to therefore drop this operator algebraic story. Now, what I want to keep at least 2 of these axioms in some form. Now, I'm going to drop the first one because I'm working with chain complexes. So this would be like injective morphism of algebras. It's not a good notion for chain complexes. So the first axiom is going to go. So instead, I'm going to say that there is some local to global property, or all A of O's are contained in something global. Doesn't matter how I get it. So there is some global algebra. Okay, so that I can make sense of this commutation. Moreover, so now I go to this axiom. There is this nice, commutation at space-like distance. This might be too much. Why? Because this is something that should hold for observables, okay? Things that we can observe, or at least in principle talk of them as observables. But in the BV formalism, we will have maybe some auxiliary and physical fields. There is no good reason to expect all these auxiliary objects to actually satisfy this axiom. So I'm going to say that this holds on the level of cohomology. So we are working with chain complexes. So I'm going to say causality T on cohomology. Okay? And I still have enough space to talk about the last one. So the last, yes? Question? No. So the last one, this is this ugly equality that I'm going to get rid of. So there, I'm just going to ask for a quasi-isomorphism. So this replaced by quasi-iso. Okay, so that these have to be notions that make sense for chain complexes. Okay, maybe I put it up so that people can see it better. And that's the framework. So now I'm going to spend the rest of this series of lectures telling you how to construct models. That's what it is about. And this is where BV enters. Yes, John? That's correct, yes, up to chain homotopy. Yes, yes. That's another nice way of saying it. Mm-hmm. Up to chain homotopy. No, I want them to be sitting in the same. Well, I want to be able to talk about. I want them to map into something global so that I can make sense of this. Of this commutation at space-like distance. So there has to be some notion of a global algebra that, I get, let's say, from gluing these local things together. Oh, yeah, sorry, no, that's a bad thing. Okay, that's not, maybe that's not, okay, sorry. So somehow, let's just say that really what I want is some local to global property so that the second axiom makes sense. That was a bit strong. Well, 1, 2, Fine. Yeah. Right. Yeah. Yeah, maybe. That definitely is an example. I mean, the example which I'm thinking about of a local to global property, I would ask this to form, or well, at least be related to some factorization algebra. So there is some, I mean, you're familiar with that, right? So, but I don't need to commit to that. So. Yeah. On cohomology level, I would expect an embedding. Yeah, so on the cohomology level, so I want this to be sort of weak version of the usual AQFT story. But having some local to global property is actually quite good. So maybe for people who know that, let me say, for example, a factorization algebra structure. Okay, and again, depending on how things go, I might want to say that in the last lecture. So how to get that factorization algebra structure. Do I need what? Why?
You might have a non-trivial observable locally.
Yeah. Okay, I mean, it depends. I mean, okay, so this, of course, you can generalize things, okay? I mean, you can say, okay, well, let's drop it entirely, right? Let's drop it entirely. I'm not particularly married to a given set of axioms. But in the examples I'm going to talk about, this actually is true. This slightly stronger property is true. But yeah, I'm not going to set it in stone here. This is vague on purpose because, as you go away from this strict picture, there is, if you want to, say, recover the strict picture on the cohomology level, then you want to ask for these to give you embeddings on cohomology, all right? So that's the sort of situation I'm talking about right now. But then, of course, if you drop it entirely, then you can talk about a larger class of models. That, axiomatic systems are there essentially to organize your thinking about something. It's not that, like you say that reality is a Hackasler axioms or something. So it's very much dependent on what we want to prove and what models you're talking about. Okay, but anyway, this is just to give you some idea of what I'm going to construct, but I'm really interested in constructing models rather than inventing axioms. The clever people who invent axioms all the time. I don't have to do it. Okay, so constructing models. Oh, and how much time do I have? What was the end point of this?
So it's 1 hour and 50 minutes.
Uh-huh.
Typically 5 minutes break in somehow 35 minutes.
Cool.
30 minutes, depends on where.
Depending on where, okay, good. So constructing models. I have a space-time. Now, somehow I want to construct those algebras. So I will start with vector spaces before I get to algebras. So, okay, so I'm asking then, somebody who ordered the model to be constructed, what type of fields do you want, right? Do you want a scalar field? Do you want Young-Mills? Because Alberto, I'm sure he would enjoy it. Do you want perturbative quantum gravity? I had somebody order them as well. So yeah, I need to know what are the fields. So part of the sort of input here is, so input. Okay, so space-time. Then what fields did you order? So for the sake of this talk, I'm only taking the orders for fields that are smooth sections of a vector bundle. Okay. This is actually, well, it is clearly a vector space. This is, it can be equipped with a nice topology. So I was talking about topological vector spaces as sort of something I want to get. So this comes with natural fresh air. Where does the thing go? Sorry, first one, yeah. And which direction? I'm dyslexic. I don't do writing. If I manage to not confuse E with number 3, then we can call this lecture an incredible success. Okay, so this comes with the natural Fréchet topology. So that's going to be useful for trying to say what it means to, have functions on that are differentiable, smooth, and so on. So it's not completely irrelevant. Okay, so what else do I need? Okay, so maybe I should write the examples. So examples, scalar field. So then E would be just smooth functions on M, real valued, and Young-Mills. Then E, and let's look at the trivial bundle situation for simplicity. So these are one forms valued in some Lie algebra. So things like that. Okay, and now I want to have some sort of observables. So first, classically, how do I think of observables? Where I have a field, an element of that space of field configurations. I perform a measurement and I get a number, right? I can be measuring some property of the field. So in the first instance, classical observables are some functions of the fields. And for mathematical convenience, I'm going to talk about smooth functions. So observables modeled, or classical, I should say classical observables modeled as smooth functions on the space of field configurations. And again, for future convenience, I'm going to make them valued in complex numbers. Actual, things that you can observe would be self-adjoint with respect to the conjugation, so real numbered, real valued. So the actual, let's say, physical observables would be in this. But it's useful to leave us a bit more space for future convenience. All right, this is clearly too much. This is a big space, a lot of mess. You're probably not going to need all of that. So when you think about quantum field theory, if you think about, back about Pavel, for example, he wrote all these nice Lagrangians and things like that. These are very particular functionals, very specific, that can be written as functions of the fields and their derivatives at the same point, right? And then you integrate. So these are called local functionals. So in particular, I have local functionals, all right? Okay, and these are functionals of the form that f of phi, and phi is always going to be a field configuration. It doesn't mean I'm doing only the scalar field. It just means I cannot do indices. So this is an integral over the whole manifold of some function. So either you can say it more precisely and say this is a function of a cave jet of phi integrated with some volume form, or you can be more down to earth and say this is a function of the field and its derivative up to a fixed order. So function of phi of x with some indices d phi of x and so on up to order k. So these are local functionals. All right. And now we want some algebras. Local functionals from a vector space, you can add them, but they don't form an algebra. So I have to, give them some sort of a product. So actually, there's an obvious product on the space of functions. Pointwise product. So f product g of phi. This is defined, so it all maps to numbers. So I can just take the product of two complex numbers. That's allowed. Sorry, my notes are running away. I should keep them in a better place. Okay, and now I can take the algebra generated by local functions with this product. So f is going to be multi-local functionals. Okay, and this is algebra generated by f log with respect to the product, which is this pointwise product. And this is going to be my main playground for things. There is another space I'm going to use a sort of auxiliary tool. Before I state that, let me maybe come back to this symbol that nobody asked about, but you should. What do I mean by smooth? It is infinitely many times differentiable, and differentiability is defined in terms of this Frechet topology on E. And then you want to say, what does it mean to be continuously differentiable? So let me maybe give this a bit more flesh before I continue. So a functional derivative, and this is also introducing some notation that I'm using. So a functional derivative is defined as the directional derivative. Okay, so 1 over t and then f of phi plus sigma minus f of phi. If exists, oops, that should be t. If exists. Okay, and then continuously differentiable would mean continuously differentiable so this derivative is a map from E. This is where this comes from. And now this one, so that's the direction, which is also an element of the configuration space. So that's a product space. Two complex numbers. This has product topology. Product topology. So this has to be continuous function. So then you say continuously differentiable. And then you iterate, and this is how you get smooth. So iterate to get C infinity. So in particular, this is a nice situation. Our space of field configurations is a space of smooth sections itself. So then continuous maps on the space of smooth sections give us distributional sections. Okay, if you had some course in functional analysis or similar, you might know a bit about distributions. So distributions, you know, in physics we like distributions a lot, right? Because Dirac delta is a distribution, all the propagators are distributions. People sometimes call them generalized functions. You can do distributional sections as well. So they also live in the dual of the space of smooth sections. So why am I talking about it? I'm talking about it because I wanted to say that the nth derivative at a point is an element of now the space of distributional sections. So this is the continuous dual. So this dash is the continuous dual. So n derivative, so we have n directions. So the fiber is going to be the nth exterior tensor product over mn, okay? So the dual of the space of smooth sections like that. And these are usually, you know, as nasty as you want. Now, sometimes you're lucky, and this distribution actually turns out to be not singular at all, and it turns out to be a smooth section. So in this space, you have the space of, now careful that this doesn't have support restrictions, so this has to have support restrictions, compactly supported sections of the dual, okay, n over mn. So there is an embedding of this space into that. So C means compactly supported sections. Okay, so now I can define the space of nice functionals. The nicest functionals that you can ever get are those whose derivatives are actually smooth. So they don't cause trouble. They are also completely boring, but I will use them as a sort of toy model to get things started. So space of regular functionals are such that all these derivatives Fn of phi are smooth So leaving that space of sections of the dual are smooth. All right, so I have essentially all of the pneumatical structure, and the next step is to introduce the dynamics. So that I think it makes sense to make a break here. What do you think? Is this the normal time for break, or? Yeah, I guess. Yeah, maybe let me just talk a bit about the dynamics and then I make a break. So just to have at least the sort of introductory part over with. So dynamics, okay. So that is introduced using the Lagrangian framework. And again, I almost want to do what Pavel did, but you assumed your manifolds to be compact, which was very good. It's great, but the manifolds I'm working on are not compact, so I have to do something slightly different. So here I'm going to work with Lagrangians with a cutoff. So the cutoff is going to be kind of, for people with physics inclinations, infrared cutoff. So it's going to render my integrals of, Lagrangian densities well-defined, finite. So Lagrangian, or let's call it the way I usually do, generalized Lagrangian. L is a map that takes a cutoff function. So I'm going to use this notation, Schwartz notation D, which is smooth, compactly supported function on M. So it takes F, which is an element here, and assigns to it L of F, which is a local functional. Okay? So that's what the generalized Lagrangian is. So again, examples, free scalar field, L of F of phi, that's maybe 1/2 d mu phi minus m squared phi squared. Okay, and let's say Young-Mills. So, and then there are going to be some, maybe let's say like this one. So F wedge star F. Okay, so where F is dA. Okay, so that would be bad, right? F has to be somewhere here. So I put F here, and I put F, for example, here. Okay, this is just a cutoff, it's just multiplying the Lagrangian density. Nothing bad happens. So then I can try to, well, first of all, it would be very silly if I couldn't get rid of that cutoff. It's not really physical. Using it is justified by the fact that I'm actually interested in constructing local algebras. Okay, so somehow I want to say that I can always choose a cutoff large enough, okay, so that my local observables don't see it, they don't care. So actually, maybe I need to find a precise way of how to localize, those functionals. I mean, I said they were local, right? But it doesn't really mean that, they are localized in a particular region. So I need some notion of assigning these functionals to regions. So I need another definition. So I will define the support of a functional. So this is defined as a space of all x in M, such that for all neighborhoods open of X, there exist phi and psi configurations in support of psi contained in O, such that f of phi plus psi differs from f of phi. Okay, so these are sort of the region of space-time where my observable, my functional is sensitive to perturbations supported in that region. So, okay, so that defines me localization of functionals. Okay. So yeah, so now I want to say, well, all right, so I'm going to make this, well, define the dynamics using this Lagrangian. I'm going to consider, again, some sort of variation of this, so take a derivative, as we did for the observables, but then I want to be sensitive to the fact that maybe actually I'm only interested in perturbations in some fixed region, and then the cutoff could be taken to be 1 in that region. So locality is super important somehow in this context. So again, define, so there is always a lot of definitions to get things started. So the Lagrange derivative, or the Lagrange derivative, dl, okay, of phi in the direction of psi, so phi is in E, psi is going to be a compactly supported section, compactly supported. All right. So this is, I take L of f for some f. I assume f to be identically 1 on support psi of phi in the direction of psi. Okay, and sorry, that should be first derivative. So I take the variation of L of f in the direction of psi, and I choose this cutoff to be 1 on support psi. That definition, because of locality, this doesn't depend on f, on the choice of f, it depends on the choice of f, and it defines dl as a one form on the space of configurations, and defines df as an element of now one forms on the space of configurations, complex valued. So we are sort of one level of abstraction higher. We are talking about now sort of geometry on the configuration space rather than on the manifold. And this one form is going to give me the dynamics, the equations of motion. Okay, so the equations of motion, or the equation of motion, actually there's just one equation, unless we write it in components, but we don't have to, is like this. So dl of phi equals 0, so solutions, okay, so these form the space ES, which is actually, well, by definition, right, this is the zero locus of that one form, is the zero locus of dl. Okay. Yep.
This is also true for the compactly supported function psi, right? Because if psi is not compactly supported, then there's no f that is
No, this, okay, so this is a definition. Let's see. So you're saying, let's look at this. So psi is compactly supported, right? So this is an element of this space of compactly supported sections, right? This defines me dl as something in the dual, right? So this defines me dl of phi as an element of EC prime. You agree? EC prime is the space of all distributions not necessarily compactly supported. So DL is not necessarily compactly supported. Yes?
Because in perturbative theory, we are interested in S metrics, for example.
Yes.
If we don't include the size that are not compactly supported, then we can't see S metrics.
No. I think we don't understand each other. So this is defining you the variation, the Euler-Lagrange derivative, the classical Euler-Lagrange derivative, the variation of the Lagrange, and this is classical. Okay, so psi is here a perturbation, so phi is not compactly supported, psi is a compactly supported perturbation of the field. Okay, so in a sense, you can think about it, you can take, ooh, it's raining nicely. You can take the tangent space to the space of your field configurations, where the tangent direction is restricted to compactly supported things. And then one forms would be the dual of that. So DL is a one form of that sort. So DL knows about classical dynamics without support restrictions. Okay, I can give you an example. So example. So let's take, again, this free scalar field that I erased. So L0 free scalar field. Okay, and then dL0 of phi, this is minus D'Alembert plus m squared on phi, where phi is obviously arbitrary. Right? So phi is arbitrary. This is a differential operator. Right? So this is an example. And you get the usual equations of motion of classical theory this way. Now, okay, you mentioned S matrix, so either you know what's coming next in my lecture, or you connected this. I'm going to talk about S matrices as well, but there is this little trick by Epstein and Glaser from 60s, 70s, that you introduce a cutoff for your Lagrangian, construct something called a generalized S matrix or a local S matrix, work with that, and then take the adiabatic limit where you remove the cutoff. Okay, so you're thinking about quantum theory, which is great. So you're thinking about this cutoff as sort of infrared cutoff in quantum theory. Okay, this is fine. At the end of your calculations, you would take the limit f going to 1. Right? And the reason why this is going to be harmless is that this is not going to affect the correlations of local fields. Correlations of local fields are going to be indifferent to how I take that limit. Does it make some sense? I mean, there will be more to that later. Any other questions? Yes? It's not a linear function. It's not a linear. It doesn't have to. This is a linear function in the examples, but it doesn't have to be a linear function.
So what's an example where it's nonlinear?
Oh, you can take f squared. No, I mean this is silly, but in Glaser framework, you think of f as space-dependent coupling constant. So you take your coupling constant, say lambda, right, and then you replace the constant with a function. And then, of course, if you have like higher powers of the coupling, that would mean higher powers of this cutoff function.
Okay,
so it doesn't have to be that. Okay. And anything else? Okay, I think it's a good time to make a break. So you can ask more questions during the break, of course. Thank you. Okay, so I hope you enjoyed the break and you closed the windows in your offices. Right, so this is now the point where things go a bit more BV and also a bit more cohomology. So here I said that the space of solutions is the zero locus of this one form DL. So actually you could have skip that whole story up to now and just say, well, somebody gave me one form DL, and now I want to understand its zero locus. And the way I want to do it is actually via derived locus construction. In other words, I'm going to construct the Koszul complex that provides a homological interpretation for the space of functionals on this space of solutions. And again, I'm referring to Pavel's talk for some sort of, parallels and connections, because it always helps to see things again in a different language. All right, so now I'm making this derived. So the first step, somehow I realized that, well, actually I'm interested not in this space as such, but rather the space of functionals on it. And to be consistent with that whole story, these are going to be multi-local functionals. So Fs, these are multi-local functionals on ES. So what is it? Okay, well, it's a quotient of all the functionals through the functionals that vanish on the solution space. So this is functionals that vanish on ES. And I would say we use the term vanish on shell. So we call it on shell. All right, so this I know what that is. What's that? There is an obvious example of a functional, a class of functionals that are of this form. So we have a one form, all right? So if we want to make a function, then we just contract it with a vector field. So let's take a vector field, okay? And let's make it also multi-local. So multi-local vector field. All right, so this is in particular the subset of the space of all vector fields. Smooth. And now I'm going to say, well, let's take DL contracted with X, or let me use another notation which I also like. So the insertion of DL into X. So what do we know about it, right? So for each phi of the solution space, you obviously end up, evaluating DL of phi, which is 0 by the definition what the solution space is. So this, by definition, vanishes on the space of solutions. So this is a good example of an element of F0. So actually that's not enough for me. I want to be able to say that all the elements of F0 have this sort of characterization. This requires somewhat more work and sometimes extra conditions as well. But let's assume it's true, and then somebody else has to prove it for us, or you open up, say, a book of Noah and Teitelbaum and you find it out. But as mathematicians, we can for now assume that all elements of F0 arise this way. Okay? So now I can, in other words, I can write F0 as an image of V under this insertion map. So let me now draw a chain complex, at least a part of it. So here we have essentially the 0 map. F goes to 0, everything goes to 0. Here we take this insertion, okay? So that's already good. So the image of this guy is going to be, it's going to be F0. So let's give them some labels. So I'm going to introduce some grading. I'm going to package everything I have into one space and give labels to know who lives where. Actually, let me make it a negative grading. I'm sloppy with signs, but I will at least try to keep that one consistent. So here, this map, let me denote it by delta L. So the image of delta L, when it goes from -1 to 0, so -1 to 0 is F0, okay? Now, the kernel of the map here, so the kernel of this map is everything, F. So now if I want to package it in terms of cohomology, well, you know, I have this mini chain complex here. So I could say, well, let's call it DL as well, only, you know, going from degree 0 to degree, let's say, +1. So the 0 cohomology of DL, just looking at this piece, not worrying about what else is there, that's kernel over image, so that's the space of on-shell functionals. Okay, so now I want to sort of complete this to something nicer. I want to complete this little stub of a complex into differential graded algebra. So I'm going to take all the exterior powers of V, okay? So I'm going to take the exterior algebra of V, so all the sort of, people also call it Grassmann algebra, so anti-symmetrized tensor products, together with DL, which at higher orders is extended by using graded Leibniz rule. So extend using graded Leibniz rule. Okay, so what we obtain this way, this guy is called Koszul complex. So this is, oops. So this is Koszul complex. And it, in particular, it allows us to give the space of on-shell functionals homological interpretation. So that's half of the BV story. That's the equations of motion BV story. But let's stay with this for now. There's going to be also gauge symmetries part of the story, but already here you can see a lot. So we have this space of this exterior algebra over V. This also has another name. This is the space of multi-vector fields. So V is vector fields. This is multi-vector fields. Okay, so V multivector is, exterior algebra over V, multivector fields. And as such, it comes with a natural structure of a bracket. So comes with the Schouten bracket. Again, mentioned already by Pavel. Or Schouten-Nienhuis bracket. I'm going to do it wrong. Something like that, more or less, bracket. Right? So what does it do? Well, I mean, just if you haven't seen this animal before, then it's good to have a look. So I'm going to use this notation. So if I take a vector field and a function, okay, so this is in V and this is in F, this Schouten, and I might be really messing up the signs, so forgive me. So this is going to be X vector field acting on F as a derivation. Okay, and then if I have two vector fields, then for, no, I'm giving out the conclusion. Okay, so for two vector fields, this is just the commutator. So this is X, Y vector fields. And for higher order things, I use graded Leibniz rule. So graded Leibniz rule. Okay, and so it's a nice one-shifted Poisson bracket. It's also called anti-bracket in the context of BV formalism. So this is the anti-bracket. Okay, let me make some more connections to sort of physics literature at this point. So so the anti-bracket is an important piece. Now, with anti-bracket also come the anti-fields. So let me tell you what these are in this context. So a vector field in finite dimensional situation, you can write in local coordinates using sort of derivative operators. So I'm going to use something like this, maybe a bit formally, in the infinite dimensional case. So X acting as a derivation on F, I want to write it in a physicist notation. So this is going to be X of phi at X. Okay, so the coefficient of the vector field, df over d phi of x, right? Integrated dx. That's just a notation, right, to how to write this expression. So I can think of this as an analog of, okay, so if I was writing a vector field on a finite dimensional space in the basis, I would have some sort of sum over components, right? And here instead of the sum over components, there's this integral, so something infinite. Okay, so sort of that inspires the following notation. So I'm going to write it as these coefficients multiplying a differential operator. All right, so I think of x as a differential operator of this form. And then these guys, okay, so then when I construct my space of multi-vector fields, obviously I want to build anti-symmetrized tensor products. So one way of packaging it is saying, well, these, I can think of them as formal generators that anti-commute. So I'm going to use this notation, phi double dagger of x, so I can think of it as a formal generator and call this an anti-field. So these are anti-fields. So anti-commuting formal generators. So one can unpack this definition of the Schouten bracket in terms of taking derivatives with respect to fields and anti-fields. Whereas derivatives with respect to these are going to be always left derivatives unless stated otherwise, so you can just take one off from the left-hand side. Okay, so that's some notation just to make connection to other things. Now, this bracket is actually also very useful to write this operator, this delta L. So I'm going to, well, again, with some vague hope that the signs are correct. So it turns out that this differential is almost inner with respect to that bracket. It's not quite. So let me tell you why. So dl of x is now any element of this. This can be written actually as the bracket of x with L of f. So I need to put the cutoff where f is identically 1 on the support of x. And again, the notion of the support is, well, similar for the multivector fields as it was for the functionals. It's just analogous definition. So yeah, locally you can write this differential using the bracket. Okay, so I think that more or less finishes the classical story here. We still don't have the full BV picture, but let me just take a bit of a detour again and come back to, say, more traditional PAQ with T. So we have the dynamics, and the dynamics on one hand can be packaged in terms of this complex, in terms of homological algebra, but there are also other things that you can do, and in Lorentzian setting, this is very different in Euclidean actually, in Lorentzian setting you actually have another bracket apart from this one here, which is sort of, it's not an honest Poisson bracket, right? It's a shifted Poisson bracket. In Lorentzian setting, you also have an honest to goodness zero shifted, so ordinary Poisson bracket. I want to tell you how it arises. Could actually do it more generally, but for the sake of brevity, let me jump immediately into the perturbative setting. So, perturbative setting. So I'm going to say that my Lagrangian can be written as quadratic piece plus interaction. So this is quadratic. Okay, so dl0 of phi is then differential operator because of locality. So it's some differential operator. And I assume that this operator is not that different from the wave operator. So the sort of PDE name for it is normally hyperbolic. So assumed to be normally hyperbolic. All right? So normally hyperbolic means that its principal symbol is given by the metric, namely that the highest order derivative, so the second derivative looks essentially like a wave operator, like the D'Alembert. Okay, so I can go up. And these things have a very nice solution theory. They have very nice green functions. So for such operators on globally hyperbolic spacetimes where we are working with, there exist unique retarded / advanced green functions. Okay, I'm going to denote them by GR and GA, and let me tell you what they do. So obviously they are green functions, right? So they are sort of inverses of P, of that differential operator. But what makes them retarded and advanced is support properties. So if I have a test function f supported somewhere, then I apply to it the retarded green function, then the support is propagated to the future. And if I do the other thing, then the support is propagated to the past. So this is what distinguishes them. I can slightly formally write them in terms of integral kernels, because why not? And then there is, so this uniqueness actually implies the following property. So if I write it as an integral kernel and swap y and x, I get the other guy. Okay, because if I swap them, then I get something with the support which goes exactly the wrong way, or the other way, and there's a unique guy with the support going the other way, so they have to coincide. And now I define something called the Pauli-Jordan function. Or also in my community called causal propagator. Okay, so that's why I call it GC. This is a difference between these two. So retarded minus advanced. So this is something, so this property implies that GC is antisymmetric. So GC of xy is minus GC of yx, antisymmetric. The way we wrote it here, you can see P doesn't depend on the point anymore. This is one great piece of engineering. So here, P doesn't depend on phi. Okay, so GC also doesn't depend on phi. It's antisymmetric, so you can think of it as a sort of generalized bivector field. Generalized because the coefficient is a distribution, not a smooth section, but it is a generalized bivector field. And moreover, it turns out that it's a Poisson bivector field. So this gives us generalized Poisson bivector. On E. So we can construct a Poisson bracket with that. And this construction goes back to Pius. So this is called Pius bracket. Okay, so I want to use this sort of maybe funny notation because I want to distinguish it from the anti-bracket. So this bracket of F and G is defined as follows. So take the derivative, okay, then contract it with Aha, okay, maybe not G, sorry. Bad notation. F1 and F2. Okay, take derivative contracted with GC applied to F2 derivative. Okay, so that sort of compact way of writing it, and let me write it the physics way. So this is d f1 over d phi of x, whatever indices are there, contracted with gc of xy, and then df2 over d phi of y. Okay, you can check. This is not entirely trivial computation, but you can check that this. Actually, no. But for the constant case, this is trivial. But you can define this bracket also for non-constant situation, which means that for the case that well, dl is nonlinear, right? It's depends on phi. Then you can also do that story, and you can check at home that this gives a Poisson bracket also in the non-quadratic case. So exercise, check that this gives a Poisson bracket also for higher than quadratic. L, okay. Right, so what do we want to do with this? So we have the Poisson bracket, we have the Poisson structure, and now we want to finally, after 1 hour and a half of talking, we get to quantization. So the next step, I want to quantize first the free theory, starting from the Poisson algebra, where I have this bracket as the Poisson bracket, and the product is the pointwise product of functionals. So the next step is deformation quantization. Now, again, let me make a short pause and see if there are any questions. Yes?
Is this Gaussian propagator the same thing as like the usual Feynman propagator?
No, but the Feynman propagator will come in a minute, yes. So, okay, I'm going to spoil this, but so the Feynman propagator would be related to the guy where you have a plus here instead of a minus, and it's symmetric. But yeah, it will come. Anything else? No? Okay. Quantization. That's going to be very quick. I'm using deformation quantization. Okay. So what's the idea? I'm going to introduce a non-commutative product on this space, multi-local vector fields, formal power series in H bar. I'm going to equip this with some non-commutative product, which I denote by star. First attempt. Okay, so for people who have seen Moyal quantization, then you might already have ideas, right? So I have this constant Poisson bivector. So I essentially sort of exponentiate that bracket, okay? So attempt 1, and you can see from that there will be more attempts. Attempt 1, let's say F star G. Okay, so multiplication, and here the exponential of, we want commutation relations to be with I and H bar. So let's have I H bar over 2, and here the causal propagator and with derivatives. Okay, let's do this. Quick check for h bar equals 0, the lowest order term. This is just pointwise multiplication. So f star g is at h bar equals 0 order. This is just multiplication, so good. And then another one. So the star commutator of f and g, 1 over I h bar, again at h bar equals 0, that is the bracket of g. So this has the properties I want. So what's wrong with this? Because there is something wrong with this. The problem is that this is singular, and the derivatives of f and g are also somewhat singular. So this is going to be only defined for this more restricted class of functionals, namely the regular ones. So here, I want to say that f and g have to be in f regular. Okay, but that's not enough. We want to make sense out of this for all multilocal things. Or actually, you know what, I mean, let's be more generous, right? I mean, we can make vector fields here as well, but it's the regularity which is the problem. So one can fix it. One can fix it by modifying this integral kernel in the exponential a bit. So fix this by the following. So let's define g plus as I half gc, so this is what we had before, plus some symmetric part h. So this is symmetric. Okay, and this, you remember, is purely anti-symmetric. This, adding a symmetric part, doesn't ruin the commutator, so we keep everything. And also, obviously, it doesn't ruin the zeroth order property. So we kept those two properties, but now we have a bit more freedom. And it turns out that, in fact, this is very, very useful. So we can choose h in such a way that the singularity of g plus will be much, much tamer than the singularity of gc. So choose h such that the singularity structure of g plus. So the nice condition is that it looks like the Weidmann two-point function in the vacuum. So the singularity structure looks, okay, I'm going to put it in quotation marks, looks like the one of the vacuum two-point function. This, well, people would call it, this is normal ordering. This is normal ordering. I mean, you can think of normal ordering as sort of pre-renormalization, but yeah, this is normal ordering. That's correct, yeah. So for people who know the terminology and heard that before, so this is Hadamard, or this is actually two-point function of a Hadamard state, and this looks like is a wavefront set condition. So if you've done a bit more with distributions, then, you know, just just definitions and a few properties. You might have opened the book of Hermander once or twice. The way to nicely characterize the singularity structure of distributions is using wavefront sets. So this satisfies a wavefront set condition. Okay. And that wavefront set condition, so that extra piece of freedom that allows us to fulfill it, that actually is enough to make that product well-defined on multi-local functionals and more generally multi-local multi-vector fields. That's a silly name. Yes? It is. It's because this is, you see, this is constant Poisson bivector. So that's obvious.
Even when you add the symmetric part.
Yeah. So the symmetric part is still point independent. It's still constant. So that's safe. So attempt 2, and this is the final attempt. We say that F star G, sorry, I lied to you, it's actually this one. So H bar G plus D over D phi tensor D over D phi F tensor G. Okay, so that is a good definition. So F and G can now belong anywhere in this space of multi-local, multi-vector fields. This also doesn't depend on anti-fields at all. Okay, this is completely oblivious to what happens in the anti-field direction. And just to give you a word of caution, this choice is not unique. Okay, so there are many possible ways of adding this symmetric term so that we can get a right wavefront set. So this is just a remark. The choice of H is not unique. But it turns out, well, this is also maybe an exercise for the audience. You can easily check that star products with different choices of H give you isomorphic algebras. But the algebras are isomorphic. So that's good enough. Okay. So that's more or less the free theory. So we still have some time before we finish for today. So I can actually start talking about the interaction, which is, the fun part of quantum field theory. So we finished quantizing the free theory, now the interaction. Okay. So I want to remember that they had this interaction term, and this can be obtained, this can be realized, actually using to a large extent intuition from path integral. So I'm going to use a lot of sort of path integral intuition and maybe some heuristics, but not the actual fact that they are integrals, okay, because they're not. So it's more like an inspiration. So here, first of all, I opened my, any quantum field theory book and look what people do when they want to construct interacting fields. And you find, for example, the formula for the interacting fields in terms of a path integral S matrix, correlation functions, and things like that. So this is somehow something I'm going to package right now. And the first, maybe one of the first things you discover when you start digging into interacting theory is Feynman propagator. So Feynman propagator is going to be a big hero of this part of the lecture. So let me first define what it is. I'm slightly more general than just a flat spacetime, right? Because on Minkowski, everybody knows what's the Feynman propagator. But now I'm on general curved background. M is just any globally hyperbolic spacetime. So it might not be obvious what's the Feynman propagator. For me, the Feynman propagator is a close cousin to this G plus, which differs only by having a plus between the green functions. Okay, so that's the Feynman propagator. With that gadget, I can now attempt to define a product. So, definition is something called time-ordered product. All right, so again, attempt number one, I'm going to take F and G, which are regular, okay, because last time something terrible happened, so I want to make sure that, I take things slowly. So let's do that. Let's just insert the Feynman propagator instead of G plus. Let's do GF. Great. And then those derivatives. All fine. F, G. Okay. Let's start with the good things. So the good things, the following. So this product is commutative. It's closely related to both pointwise product and the star product in different ways. So let's give the relation to the star product that justifies the name time-ordered. So F time-ordered G is F star G if the support of F is not earlier than the support of G. Okay? Not earlier that. So F not earlier that G. And it's the other way around if they are the other way around. So it really is the time ordering of the star product. This is the time ordering of star. Okay, so that's one nice thing. The other nice thing was the relation to the pointwise product. So define the following. So the time ordering operator is H bar half G Feynman d squared over d phi squared. Using this, you can write the following. So F time ordered G is T minus 1 F pointwise T minus 1 G. So it's actually equivalent in this sense to the pointwise product. So equivalent to pointwise product. All right. So what do I want to use it for? I want to use it to define something that I announced at the beginning, namely the local S matrix. So use this to define local S matrices. Okay, so again, we are looking at these interactions with a cutoff. So S of V, where V is regular with compact support. Okay, this is defined as the time-ordered exponential of V. So this is, in other words, I can write this as T composed with the usual exponential composed with T minus 1 of I over H bar V. Okay. Aha. So that's something slightly related to physics language. I give you one better. I can also define interacting fields. So interacting, or maybe more precisely, interacting observables. Okay, so if I want to compute the correlators of interacting observables, this will come in handy. So there is a map RV acting on classical observable F. Okay, so this is given by S of V, and here inverse with respect to the star product. So this is star inverse. Okay, times S of V time ordered F. This, people might recognize it, is the Bogolyubov formula. For the interacting fields. All right. So with the content of this board, I essentially solved, the problem of constructing interacting models. I have these interacting observables. I can now go ahead, find the state, compute correlators. What stops me, right? So people who heard me talking before obviously know what stops me. I made this assumption a while ago. So everything I wrote here is actually only true if I assume all the functionals, all the observables to be regular. Okay, why is this a bad idea? Okay, let's think this is another exercise to the audience. What functionals are both regular and local? Let's try to think about it for a sec. So how badly did I really restrict myself? So from quantum field theory, interactions are local, right? Observables are local, so we want local things. I assumed things to be regular. So all the derivatives have to be smooth. So let's take a functional which is just an integral of a field with f, okay? The first derivative is just f, second derivative is 0, it's all fine. So this is regular. And phi is, this depends only on one thing, right? So it's very trivially local. Okay, so that's an example of something that's both regular and local. So let's take quadratic. So take f of phi, say phi squared, smeared with a test function. It is local. Is it regular? Okay, so I differentiate once, then I would have phi of x times f of x. I differentiate twice, and what do I get? I differentiate twice. This doesn't depend on phi actually anymore. I get f of x times the Dirac delta of x minus y. You can check it at home. Now that's not very regular, okay? This is not smooth. So not regular. Okay, so that's bad. So it only gets worse. So the only things that are both local and regular and linear functionals, and if I could only quantize linear interactions, you would be badly cheated in this course. So I have to do something about it. So these formulae are very nice, and I like using them as a sort of algebraic, testing ground for ideas. But one has to do something. And that something is called renormalization. So we know from quantum field theory, sort of traditional quantum field theory that you find in Peskin-Schroeder, that things need to be renormalized. Singularities are actually pretty bad in QFT. Something has to be done. So the next step for me then is to try to reconstruct that story with the time-ordered products, S matrix, and the Bogoliubov formula in the way which includes renormalization. So this is going to be now a preview for the next time. So and it all has something to do with the fact that Feynman propagator is very singular. Okay, so this is the singularity structure of the Feynman propagator that makes it absolutely necessary to, fix these time-ordered products somehow. So now, the way I want to phrase this problem, I want to extend T, the time-ordered product, to multi-local functionals and, well, also multi-vector fields. This problem, this extension problem, this is the renormalization problem. And the renormalization solution is that of Epstein-Glaser. Okay. So what I'm going to do next, I'm going to fix those time-ordered products so that we get a nice renormalized theory, and then show you what happens to the BV operator that you might have forgotten by now because it was a long time ago, but I'm going to come back to it as soon as I renormalize everything. All right, I think it's enough. Let's start renormalization at the beginning of next lecture, and thank you very much for your attention. Questions? Mm-hmm. Not yet, because you see, already phi squared is non-regular, right? So phi fourth is even less regular.
No, I mean, except the lecture.
Sorry?
Except the lecture.
Apart from the lecture, which is the status.
Sorry. The status is that there is a result saying that phi to the fourth is trivial. Not your best interacting theory to choose. I mean,
From the BV formalism, we know that phi for sure doesn't exist, that it's not UV-free, but I just wanted to know if there's a solution here.
well, this is perturbative. All of this is perturbative. I don't make any statements about non-perturbative theory. Right, so you can construct things perturbatively that you do not expect, or you might not be able to construct non-perturbatively. So if you want to talk about triviality of phi to the fourth in 4 dimensions, right, you need to be really looking at non-perturbative settings, so like people do in constructive quantum field theory. This is sort of different call of the woods. This is more focusing on the structure of perturbation theory itself and packaging it using, say, the BV formalism and, in this case, Epstein-Glaser, but makes no statements about non-perturbative setting, if that makes sense.
Other comments? Questions? Well, then let's thank again the speaker.